What if I told you that empty space is not empty? Not just metaphorically, not philosophically, but physically. Right now, in the space between you and your screen, countless particles are appearing and disappearing out of existence. The vacuum around you is boiling with activity. And according to some of the most successful theories ever created, reality itself may not be smooth. Space could be made of tiny quantum pieces. Time might emerge from something deeper. And the universe you experience every day could be built from information rather than matter. The strangest part, these ideas are not science fiction. They come directly from the mathematics that powers modern physics. Today we're diving into one of the deepest mysteries in science, the strange physics of quantum space, a journey into a world where emptiness has energy, where distance may be an illusion, and where the fabric of reality behaves in ways that challenge everything we think we know. The biggest illusion in the universe. Take a look around. The floor beneath you seems solid. The walls seem solid. Your body seems solid. Space itself seems smooth and continuous. But physics has a habit of exposing illusions. A table feels solid because the electrons in your hand repel the electrons in the table. Atoms are mostly empty space. Matter itself turns out to be stranger than our senses suggest. And now physicists suspect that space may also be hiding a deeper reality. For centuries, people imagined space as an empty stage where events happen, a giant cosmic container. Objects moved through it. Stars floated inside it. Galaxies occupied it. But then came Einstein. Einstein showed that space is not a passive background. Space and time combine into something called space-time, and space-time can bend. Massive objects warp it. Planets orbit stars because they follow curves in space-time. Black holes are regions where space-time becomes extremely distorted. Suddenly, space was no longer an empty box, it became an active participant in reality. Yet Einstein's theory described space-time as smooth, continuous, like an infinitely stretchable fabric, and this is where the trouble begins, because another theory tells a completely different story. The quantum revolution. Quantum mechanics is arguably the most successful scientific theory ever created. It predicts the behavior of atoms with astonishing accuracy. A smartphone in your pocket exists because quantum mechanics works. Lasers work because quantum mechanics works. Computers work because quantum mechanics works. But quantum physics paints a bizarre picture of reality. Particles behave like waves. Waves behave like particles. Objects can exist in multiple states simultaneously, and uncertainty is built into nature itself. The deeper physicists explored the quantum world, the stranger things became. Yet there was one enormous problem. Einstein's gravity theory and quantum mechanics refused to cooperate. Both are incredibly successful. Both describe reality, but when scientists try to combine them, the mathematics breaks down. It's like having two maps that accurately describe the same city, yet completely contradict each other. This conflict becomes catastrophic at extreme scales, inside black holes, during the birth of the universe, and at something called the Planck scale. The Planck scale is where reality enters territory so extreme that our current understanding collapses. And this is where quantum space begins. The Planck scale, reality's pixel size. Imagine zooming into a photograph. At first it looks smooth. Zoom further. Eventually you see pixels, tiny building blocks that create the image. Many physicists suspect space-time may work similarly. There may be a smallest possible length, a fundamental unit beyond which the concept of distance loses meaning. This scale is called the Planck length. It is approximately 1.6 times 10 to the negative 35 meters. That number is almost impossible to comprehend. If an atom were expanded to the size of the observable universe, the Planck length would still be smaller than the atom. It is unimaginably tiny. At this scale, space may stop being smooth. The geometry of reality may become grainy, discrete, quantum. We don't know for certain, but many theories suggest that space-time itself might be composed of fundamental units, tiny quantum chunks. If true, reality would have a built-in resolution limit, a smallest possible distance, a point beyond which smaller no longer has meaning. Just as a digital image cannot be divided into pieces smaller than pixels. This idea radically changes our understanding of existence. Because it suggests space isn't fundamental. It might be built from something deeper. When empty space isn't empty, now things become even stranger. Let's talk about nothing, or what physicists call a vacuum. Common sense says a vacuum should contain absolutely nothing. No particles, no matter, no activity, just emptiness. Quantum mechanics disagrees. According to quantum field theory, every point in space is filled with quantum fields, electromagnetic fields, electron fields, quark fields, fields associated with every known particle. Particles are actually excitations of these fields, like ripples on an ocean. Even when all particles are removed, the fields remain, and those fields cannot be perfectly still. Why? Because of the uncertainty principle, a fundamental rule of quantum physics. It prevents certain quantities from being known with perfect precision simultaneously. As a result, quantum fields are always fluctuating. Even in a perfect vacuum, the vacuum seethes with activity. Tiny fluctuations constantly emerge. Virtual particles appear and vanish. The vacuum is alive with quantum motion. Empty space is not empty. It is one of the most active things in the universe. And this isn't just theory. We have experimental evidence. The Casimir effect. Proof that nothing has something in it. In 1948, physicist Hendrik Casimir predicted something extraordinary. Place two metal plates extremely close together in a vacuum. Something unexpected happens. The plates attract each other. Not because of magnetism, not because of electricity, but because of quantum fluctuations in empty space. Certain vacuum fluctuations fit between the plates, others don't. This creates a tiny pressure difference. The plates get pushed together. Experiments have repeatedly confirmed this effect. Think about what that means. The force comes from empty space itself. Nothingness is exerting pressure. The vacuum possesses measurable physical properties. The absence of matter is not the absence of reality. The vacuum is a dynamic quantum environment, and this realization opened the door to one of the greatest mysteries in modern science, the vacuum energy crisis. If empty space contains fluctuations, then empty space contains energy. But when physicists calculate how much energy should exist in the vacuum, disaster strikes. The theoretical prediction is absurdly large. Meanwhile, observations of the universe show a much smaller value. The discrepancy is enormous, possibly the biggest mismatch between theory and observation in the history of science. Not 10 times wrong, not 1,000 times wrong, far, far worse. This is known as the vacuum catastrophe, and nobody knows the answer. Somewhere inside our understanding of quantum space, a profound piece of reality is missing. The universe is hiding something, and that mystery leads directly to dark energy. Why the universe is expanding faster. In 1998, astronomers discovered something shocking. The expansion of the universe is accelerating. Galaxies are not simply moving apart, they're moving apart faster over time. Something is driving this acceleration. We call it dark energy. Dark energy appears to make up roughly 70% of the universe's total energy content, yet we don't know what it is. One possibility is that dark energy is connected to vacuum energy, the energy of quantum space itself. Imagine that empty space possesses a tiny intrinsic energy. As the universe expands, more space appears. More space means more vacuum energy. The effect becomes cosmologically significant. It pushes the universe apart. This idea fits many observations, but enormous questions remain. What exactly is vacuum energy? Why does it have the value we observe? And why is it so incredibly small compared to theoretical predictions? The mystery continues, and it gets even stranger near black holes. Black holes shouldn't evaporate, but they do. For a long time, black holes were thought to be completely black. Nothing escapes, not even light. End of story. Then came one of the most astonishing discoveries in theoretical physics, made by Stephen Hawking. By combining quantum theory with curved spacetime, Hawking found that black holes should emit radiation. Today it's known as Hawking radiation. The simplified picture often involves quantum fluctuations near the event horizon. One particle escapes, the other falls inward. The black hole slowly loses energy. Over incredibly long timescales, it can evaporate. Think about the significance. An object famous for trapping everything can gradually disappear because of quantum effects occurring in space itself. Quantum space is powerful enough to alter the fate of black holes. And this discovery created another mystery, the black hole information paradox. One of the deepest puzzles in modern physics. Is space made of information? Suppose a black hole eventually evaporates completely. What happens to the information about everything that fell inside? Quantum mechanics says information cannot be destroyed, but Hawking's original calculations seem to suggest information might vanish. Physicists were horrified, because if information can disappear, the foundations of quantum theory are threatened. Decades of debate followed, and from that debate emerged a revolutionary idea, the holographic principle. According to this concept, the information inside a volume of space may actually be encoded on its boundary, just as a hologram stores a three-dimensional image on a two-dimensional surface. This sounds impossible, yet mathematics repeatedly points in this direction. Some physicists believe our universe could operate according to holographic principles. The three-dimensional reality we experience may emerge from information encoded on a lower-dimensional boundary. Space itself may be an emergent phenomenon, not fundamental, constructed from deeper informational structures. Reality may resemble a cosmic hologram. The quantum foam. Now let's zoom all the way down to the Planck scale again. What does space-time look like there? Physicist John Archibald Wheeler proposed a startling idea. At unimaginably small scales, space-time may become turbulent, wild, chaotic. Instead of smooth geometry, there could be constant fluctuations, tiny wormholes appearing and disappearing, violent distortions, rapid changes in topology. Wheeler called this quantum foam, a frothing sea of microscopic space-time fluctuations. Imagine the calm surface of an ocean from space. Now zoom in. Waves, ripples, turbulence, foam. Similarly, smooth space-time may be an illusion that emerges only at large scales. Deep below, reality could be extraordinarily restless. If quantum foam exists, then space is not a static arena. It is a dynamic quantum system, continuously fluctuating beneath everything we observe. Loops, strings, and the search for quantum gravity. Physicists have spent decades searching for a theory of quantum gravity, a framework that unifies Einstein's gravity with quantum mechanics. Two major approaches dominate the discussion. String theory proposes that fundamental particles are actually tiny vibrating strings. Different vibrations produce different particles. In this framework, space-time itself emerges from deeper structures. Another approach is loop quantum gravity. This theory suggests space is quantized directly. Instead of continuous geometry, space consists of tiny interconnected loops. Areas and volumes become discrete, like atoms of spacetime. Neither theory has been experimentally confirmed, but both point toward the same possibility. The smooth spacetime we experience may not be fundamental. It may emerge from microscopic quantum ingredients. Just as temperature emerges from molecular motion, or waves emerge from water molecules. Space itself may be a large-scale illusion generated by deeper quantum processes. Entanglement may create space. This is where things become truly mind-bending. Quantum entanglement is one of the strangest phenomena ever discovered. Two particles become linked. Measure one, the other instantly reflects the correlation, regardless of distance. Einstein famously disliked this idea. He called it spooky action at a distance. But experiments consistently support quantum entanglement. Now comes the shocking possibility. Some physicists believe entanglement may literally create space-time geometry. In other words, space may emerge from quantum connections. Distance itself could arise from patterns of entanglement. The more strongly regions are entangled, the closer they appear in space-time. The geometry of the universe may be woven from information links. If this idea is correct, then space-time is not the stage where quantum events happen. Space-time is a consequence of quantum events. Space emerges from relationships, not objects, relationships. That possibility represents one of the most profound shifts in scientific thinking ever proposed. What happened before the Big Bang? The Big Bang marks the earliest moment our current theories can reliably describe. But what happened before? We don't know, and quantum space may hold the answer. Some models suggest the universe emerged from a quantum vacuum state. Others suggest a previous universe existed before ours. Some propose quantum tunneling events that created space-time itself. There are even models where time emerges only after the Big Bang, meaning the question what happened before may not make physical sense, just as asking what's north of the North Pole doesn't make sense. If space-time itself emerged from a deeper quantum reality, then our intuitive notions of beginnings and endings may require complete revision. The birth of the universe could be a transition inside a much larger framework of existence, one we have barely begun to understand. Are we close to the answer? Despite incredible progress, physicists still do not know what quantum space truly is. We have clues, hints, mathematical fragments, experimental evidence pointing toward deeper structures, but the final picture remains hidden. Future observatories may detect tiny signatures of quantum gravity. New experiments may reveal cracks in existing theories. Advanced observations of black holes, gravitational waves, and the early universe may expose the underlying architecture of spacetime. The answers could arrive in decades, or they could arrive tomorrow. History has shown that reality is often stranger than imagination, and quantum space may prove to be the strangest discovery of all. The final thought. Right now, as you watch this video, space appears silent, empty, featureless. But beneath that appearance may lie a realm of astonishing complexity, a universe where nothingness fluctuates, where black holes evaporate, where information shapes geometry, where distance emerges from quantum connections, and where spacetime itself may not be fundamental. The greatest mystery is not what's inside the universe. The greatest mystery may be the thing that makes the universe possible in the first place. Space, the seemingly empty stage upon which all existence unfolds. A stage that may be far stranger than anyone ever imagined, and perhaps one day, when we finally uncover the true nature of quantum space, we will discover that reality is not merely stranger than we suppose. It is stranger than we can suppose. If you enjoyed this exploration into the deepest layers of reality, subscribe Into the Cosmos for more journeys through cosmology, black holes, quantum physics, and the mysteries of the universe. Because the deeper we look, the stranger the universe becomes.